The relational model underpins most of the major database systems in commercial use today. As such, an understanding of the ideas described in this unit are fundamental to these systems. Most of the remaining units of the module place a strong emphasis on the relational approach, and even in those that examine research issues that use a different approach, such as the unit on object databases, an understanding of the relational approach is required in order to draw comparisons and comprehend what is different about the new approach described. The material on relational algebra provides a vendor-independent and standard approach to the manipulation of relational data. This information will have particular value when we move on to learn the structured query language SQL, and also assist the understanding of how database systems can alter the ways queries were originally specified to reduce their execution time, a topic covered fully in the unit called Query Optimization. Let's have a look at the theoretical foundations. Much of the theory underpinning the relational model of data is derived from mathematical set theory. The application of set theory to database systems provides a robust foundation to both the structural and data manipulation aspects of the relational model. The relations, or tables, of relational databases are based on the concepts of mathematical sets. Sets and contain members, and these correspond to the rows in a relational table. The members of a set are unique, that is, duplicates are not allowed. Also, the members of a set are not considered to have any order, therefore, in relational theory, the rows of a relation, or table, cannot be assumed to be stored in any specific order. You should also note that some database systems allow this restriction to be overridden at the physical level, as in some situations, for example, to improve the performance response of the database. It can be desirable to ensure the ordering of records in physical storage. Let's now move on to the uniform representation of data. The relational model uses one simple data structure, the table, to represent information. The rows in tables correspond to specific instances of records. For example, a row of a customer table contains information about a particular customer. Columns in a table contain information about a particular aspect of a record. For example, a column in a customer record might contain a customer's contact telephone number. Much of the power and robustness of the relational approach derives from the use of simple, tabular structures to represent data. As an illustration of this, consider the information that might typically be contained in part of the data dictionary of a database. In a data dictionary, we will store the details of logical table structures, the physical allocations of disk space to tables, security information, etc. This data dictionary information will be stored in tables in just the same way that, for example, customer and other information relevant to the end users of the system will be stored. This consistency of data representation means that the same approach for data querying and manipulation can be applied throughout the system. Now, let's see a brief description on primary keys. The essential point to bear in mind when choosing a primary key is that it must be guaranteed to be unique for each different row of the table. And so, the question you should always ask yourself is whether there is any possibility that there could be duplicate values of the primary key under consideration. If there is no natural candidate from the data items in the table that may be used as the primary key, there is usually the option of using a system-generated primary key. This will usually take the form of an ascending sequence of numbers, a new number being allocated to each new instance of a record as it is created. System-generated primary keys, such as this, are known as surrogate keys. A drawback to the use of surrogate keys is that the unique number generated by the system has no other meaning within the application other than serving as a unique identifier for a row, serving as a unique identifier for a row in a table. Whenever the option exists, therefore, it is better to choose a primary key from the available data items in the rows of a table, rather than opting for an automatically generated surrogate key. primary keys may consist of a single column or a combination of columns combined together. An example of a single table column would be the use of a unique employee number in a table containing information about employees. Click on the button to view an example where we use two columns to form a primary key. Imagine a database in which we wish to store details of project tasks. Typical data items we might store in the columns of such a task table might be the name of the task, date the task was started, expected completion date, actual completion date, and the employee number of the person responsible for ensuring the completion of the task. There is a convenient shorthand representation for the description of a table. As given above, we write the name of the table, followed by the name of the columns of the table in brackets, each column being separated by a comma. Here is an example. Choosing a primary key for the task table is straightforward, while we can assume that task names are unique. If that is the case, then we may simply use task name as the primary key. However, if we decide to store in the task table the details of tasks for a number of different projects, it is less likely that we can any longer be sure that task names will be unique. For example, supposing we are storing the details of two projects. The first, to buy a new database system, and the second, to move a business to new premises. For each of these projects, we might have a task called Evaluate Alternatives. If we wish to store the details of both of these tasks in the same task table, we can now no longer use task name as a unique primary key as it is duplicated across these two tasks. As a solution to this problem, we can combine the task name column with something further to provide the additional context required to provide a unique identifier for each task. In this case, the most sensible choice for this is the project name. So, we will use the combination of the project name and task name data items in our task table in order to identify uniquely each of the tasks in the table. The task table becomes like this. We may, on occasions, choose to employ more than two columns as a primary key in a table, though, where possible, this should be avoided, as it is both unwieldy to describe and leads to relatively complicated expressions when it comes to querying or updating data in the database. Notice also that we might have used a system-generated surrogate key as the solution to the problem of providing a primary key for tasks, but the combination of project name and task name is a much more meaningful key to users of the application and is therefore to be preferred. Now, let's move on to missing information. There is a standard means of representing information that is not currently known or unavailable within relational database systems. We say that a column for which the value is not currently known or for which a value is not applicable is null. Null values have attracted a large amount of research within the database community, and indeed, for the developers and users of database systems, they can be an important consideration in the design and use of database applications. An important point to grasp about null values is that they are a very specific way of representing the fact that the data item in question literally is not currently set to any value at all. Prior to the use of null values, and still in some systems today, if it is desired to represent the fact that a data item is not currently set to some value, an alternative value, such as 0 or a blank space, will be given to that data item. This is poor practice, as of course 0 or a blank space are perfectly legitimate values in their own right. Use of null values overcomes this problem in that null is a value whose meaning is simply that there is no value currently allocated to the data item in question. There are a number of situations in which the use of null values is appropriate. In general, we use it to indicate that a data item currently has no value allocated to it. Examples of when this might happen are when the value of the data item is not yet known. The value for that data item is yet to be entered into the system. When it is not appropriate that this particular instance of the data item is given a value. An example of this last situation might be where we are recording the details of employees in a table, including their salary and commission. We would store the salaries of employees in one table column and the details of commission in another. Supposing that only certain employees, for example, sales staff, are paid commission. This would mean that all employees who are not sales staff would have the value of their commission column set to null, indicating that they are paid commission. The use of null in this situation enables us to represent the fact that some commissions are not set to any specific value because it is not appropriate to pay commission to these staff. Let's see a small note on terminology because null values, strictly speaking, are not any real value at all. We do not talk about a data item being equal to null. The logic of this is that if null does not represent a real value, then it cannot be equal to anything. This has direct consequences for the syntax and semantics of query languages of database systems that employ null values. The practical result of this is that you cannot test for whether a data item equals null. Instead, we test whether a data item is null. That is, we use the word is rather than the word equals. Another result of this characteristic of null values is that where two data items both contain null, if you compare them with one another in a query language, the system will not find them equal. Again, the logic behind this is that the fact that each data item is null does not mean they are equal. It simply means that they contain no value at all. Let's now see entity integrity. As briefly discussed before, in relational databases, we usually use each table to store the details of particular entity types in a system. Therefore, we may have a table for customers, orders, etc. We have also seen the importance of primary keys in enabling us to distinguish between different instances of entities that are stored in the different rows of a table. Consider, for the moment, the possibility of having null values in primary keys. What would be the consequences for the system? Null values denote the fact that the data item is not currently set to any real value. Imagine, however, that two rows in a table are the same, apart from the fact that part of their primary keys are set to null. An attempt to test whether these two entity instances are the same will find them not equal. But is this really the case? What is really going on here is that the two entity instances are the same, other than the fact that a part of their primary keys are as yet unknown. Therefore, the occurrence of nulls in primary keys would stop us being able to compare entity instances. For this reason, the column, or columns used to form a primary key, are not allowed to contain null values. This rule is known as the entity integrity rule, and is a part of the relational theory that underpins the relational model of data. The entity integrity rule does not ensure that primary keys will be unique, but by not allowing null values to be included in primary keys, it does avoid a major source of confusion and failure of primary keys. And now, let's have a look at foreign keys. Very often, we wish to relate information stored in different tables. For example, we may wish to link together the tasks stored in the task table described above with the details of the projects to which those tasks are related. The simplicity by which this is achieved within the relational model is one of the model's major strengths. Suppose the task and project tables contain the following attributes. We assume that task name is an appropriate primary key for the task table, and project name is an appropriate primary key for the project table. The beauty of this approach is that we are forming the link using a data item. we are still able to maintain the tabular structure of the data in the database, but can relate that data in whatever ways we choose. Prior to the development of relational systems, and still in many non-relational systems today, rather than using data items in this way to form the link between different entity types within a database, special link items are used, which have to be created, altered, and removed. These activities are, in addition to the natural insertions, updates, and deletions of the data itself. By using a uniform representation of data, both for the data values themselves and the links between different entity types, we achieve uniformity of expression of queries and updates on the data. The need to link entity types in this way is a requirement of all other than the most trivial of database applications. The fact that it occurs so commonly, allied with the simplicity of the mechanism for achieving it in relational systems, has been a major factor in the widespread adoption of relational databases. The relational algebra provides a mechanism for extracting data from a database organized according to the relational model. Some relational algebra operations require that the participating relations be union compatible. This means that the two relations involved in such operations must obey two conditions. Firstly, they must contain the same number of columns, and secondly, the values of the corresponding columns of the two relations must be drawn from the same domains. The following operations act on single relations, and therefore, union compatibility is not an issue. Note that some authors use different names for some of these operations. The alternative names are restrict, also known as select, project. The next operations act on two relations and require that the participating relations be union compatible. The operations union and intersection may be used with more than two relations. Union, also known as append. Intersection. Difference, also known as remove. The next operations act on two relations, but the relations are not required to be union compatible. Cartesian product, join, division. The relational algebra refers to a collection of operations that act on relations and produce relations as a result. Each of these relational algebra operations is described, and its use is demonstrated later. Restrict, also known as select, is used on a single relation, producing a new relation by excluding, restricting tuples in the original relation from the new relation if they do not satisfy a condition. Thus, only the tuples required are selected. This operation has the effect of choosing certain tuples rows from the table, as illustrated in the diagram. The use of the term select here is quite specific as an operation in the relational algebra. Note that in the database query language SQL, all queries are phrased using the term select. The relational algebra select means extract tuples which meet specific criteria. The SQL select is a command that means produce a table from existing relations using relational algebra operations. Using the relational algebra, extract from the relation singers those individuals who are over 40 years of age and create a new relation called mature since E equals singers roles.